NASA's newest map stitched together hundreds of surveys into a single portrait of the cosmos, revealing patterns we never imagined. Stay tuned, because the #1 map will completely reshape how we view our place in the universe. Imagine a map that captures the faint afterglow of the Big Bang across the entire sky, stitching together data from COBE, WMAP, and Planck into one seamless image. This composite reveals temperature variations as tiny as a few millionths of a degree, allowing scientists to infer the universe's age, composition, and geometry. By overlaying these subtle ripples, researchers can test theories of inflation and dark energy with unprecedented precision. The visual impact is striking, swirling blue and orange patches that hint at the primordial seeds of galaxies. Up next, #9 will show how billions of individual galaxy observations merge into a single evolutionary tapestry.
Surprising as it may sound, this mosaic blends over 3 million galaxy images from the Sloan Digital Sky Survey, Hubble, and the Dark Energy Survey into a single, time-sequence portrait of cosmic evolution. Each galaxy is color-coded by its redshift, creating a flowing river of light that stretches from the nearby universe to its farthest observable reaches. The map highlights how star formation rates have risen and fallen, and it pinpoints epochs when massive galaxies assembled most rapidly. Researchers use this visual to trace the large-scale structure, filaments and voids that shape the cosmos. Coming up, #8 uncovers the hidden scaffolding of dark matter that underlies these luminous structures.
Over the past decade, scientists have combined gravitational lensing measurements from dozens of telescopes to chart the invisible web of dark matter that threads the universe. This atlas translates subtle distortions of background galaxies into a three-dimensional density map, revealing massive halos where galaxies cluster and vast emptiness elsewhere. The result is a ghostly, filamentary network that explains why galaxies form where they do. By visualizing the scaffolding, astronomers can test competing theories about dark matter's nature and its role in cosmic expansion. Next, #7 will guide us through the precise locations of thousands of known exoplanet host stars.
Few people know that NASA's Exoplanet archive now feeds a comprehensive sky map pinpointing every star confirmed to host a planet. This map layers data from Kepler, TESS, and ground-based observatories, using color and size to indicate planet type and orbital period. The visualization uncovers clusters of potentially habitable worlds near the galactic habitable zone, and highlights regions still underexplored. It also serves as a guide for future missions aiming to image these distant worlds directly. Up next, #6 reveals a breathtaking panorama of interstellar dust clouds that shape star birth across the Milky Way.
Hidden in the glow of infrared surveys, this panorama stitches together data from Spitzer, Herschel, and the Wide Field Infrared Survey Explorer to expose the sprawling dust lanes that veil star-forming regions. The resulting image showcases towering filaments, dark voids, and glowing pockets where new stars ignite. By mapping dust density and temperature, astronomers can predict where the next generation of stars will emerge. The visual also illustrates how dust influences the chemistry of planetary systems. Coming up, #5 will illuminate the most active stellar nurseries captured in a single composite.
Deep beneath the galactic plane, astronomers have merged ultraviolet, optical, and infrared observations to create a composite of the Milky Way's most prolific star-forming complexes. This image juxtaposes the bright, ionized gas of H2 regions with the cooler, dusty cocoons that hide newborn stars. It highlights iconic sites like the Orion Nebula and the Carina Nebula, while also revealing lesser-known pockets of activity. By comparing different wavelengths, scientists can track the life cycle from dense cloud collapse to stellar ignition, offering insights into the efficiency of star formation across environments. Next, #4 will catalog the remnants of stellar explosions that have shaped our galaxy.
When massive stars end their lives in spectacular explosions, they leave behind glowing shells of gas and dust. This census compiles high-resolution images from Chandra, Hubble, and radio arrays to map every known supernova remnant in the Milky Way and nearby galaxies. Each remnant is color-coded by age and composition, allowing viewers to see patterns of where recent supernovae have enriched the interstellar medium. The visualization helps researchers understand how these events seed future star formation and influence galactic chemistry. Up next, #3 will plunge into the mysterious realms surrounding black holes.
Remarkably, by integrating data from the Event Horizon Telescope, X-ray observatories, and theoretical simulations, scientists have assembled a gallery that visualizes the surroundings of dozens of known black holes. The images depict accretion disks, relativistic jets, and the warped spacetime that bends light into eerie silhouettes. Though the actual event horizon remains invisible, these composites provide the closest visual approximation to the edge of no return. They also illustrate how black holes affect their host galaxies, from feeding on surrounding matter to launching powerful outflows. Coming up, number 2 showcases a detailed 3D model of our own solar system's terrain.
Finally, NASA's planetary missions have produced a unified three-dimensional terrain model that stitches together topographic data from the Moon, Mars, Mercury, Venus, and the icy moons of the outer planets. By merging laser altimetry, radar, and photogrammetry, the model lets viewers rotate and explore craters, canyons, and volcanic plains across the solar system as if they were a single, interconnected world. This comprehensive view highlights comparative geology, showing how impact rates, tectonics, and erosion differ among worlds. The model also serves as a training ground for future explorers and a baseline for detecting subtle changes over time. And now, number 1 reveals the ultimate all-sky multispectral map that unites every survey into a single cosmic portrait.
And finally, the All-Sky Multispectral Universe Map merges data across the electromagnetic spectrum, from radio waves captured by the VLA to gamma-ray bursts recorded by Fermi, into a single, interactive portrait of the cosmos. This unprecedented synthesis overlays hundreds of surveys, allowing users to toggle between wavelengths and see how different phenomena appear in each band. The result is a dynamic atlas where galaxy clusters glow in X-ray, star-forming regions blaze in infrared, and pulsars flash in radio, all within the same frame. Researchers can now cross-correlate features instantly, accelerating discoveries about the universe's structure and evolution. This map embodies the power of collaboration, turning isolated datasets into a unified vision that reshapes our understanding of everything from dark energy to the birth of stars.
We've traveled from the whisper of the cosmic microwave background to the intricate 3D terrain of our own solar system, witnessing how NASA's data-driven art reshapes our cosmic perspective. Each map not only visualizes science but also inspires new questions about the universe's past and future. If you enjoyed this journey, subscribe so you never miss the next mind-blowing list, new discoveries explored every week. Which map surprised you most, and why? Let me know in the comments, and if you liked the video, give it a thumbs up. Thanks for watching.